How to predict modulo-N counter output sequences. Imagine you're watching a digital clock or a counter in a game show, and you wonder how it knows when to reset. That's where understanding how to predict the output sequence of a modulo-N counter comes in. These counters are everywhere in electronics, from simple timers to complex digital systems. So, how do we figure out what sequence they produce? Let's break it down step by step. First, you need to know how many flip-flops are required. The rule is simple. Find the smallest number of flip-flops so that 2 raised to that power is equal to or greater than n. For example, if you want a counter that counts up to 10, you need at least 4 flip-flops because 2 to the power of 3 is 8, which is less than 10, but 2 to the power of 4 is 16, which covers all numbers up to 15. This way, you can representing all states from 0 to n-1. Next, think about the counting sequence itself. Usually in binary counters, the sequence is just counting from 0 up to n-1 in binary form. But remember, a modulo-N counter can be designed to follow different sequences or patterns, not just natural binary. It might skip certain states or follow a specific cycle, depending on how it's designed. Now, create a diagram showing how the counter moves from one state to the next. This is called a state diagram. It helps you visualize the sequence and see how the counter cycles back to 0 after reaching n-1. Assign binary codes to each state based on the number of flip-flops you decided on earlier. This assignment makes it easier to understand the transitions. Once you have the states, you need to determine what signals are needed to make the flip-flops change from one state to the next. This depends on the type of flip-flops you are using, whether they are T, JK, or D flip-flops. You can use an excitation table for each type, which tells you what inputs are needed to cause the flip-flop to change states correctly. After that, simplify the logic needed to generate these inputs. Use Boolean algebra or Karnaugh maps to reduce the complexity of the logic expressions. The goal is to make the circuit as simple as possible, which saves cost and makes it more reliable. Connect these simplified logic circuits to the flip-flops, and you will have a working counter. Predicting the output sequence then becomes straightforward. Start at 0, and each clock pulse moves the counter to the next state. When it reaches n-1, it resets to 0 and repeats. If the counter is synchronous, all flip-flops change at the same time, making the sequence predictable and stable. Asynchronous counters change one flip-flop at a time, which can cause delays and glitches, making prediction trickier. When n is not a power of 2, you need extra logic to reset the counter early once it hits, and this involves decoding the states to detect when the count reaches n and then forcing a reset. This way, the counter only counts through the desired n states, skipping the unused ones. These counters are used in many applications like digital clocks, frequency dividers, and control systems. They help in designing systems that need specific counting ranges rather than just binary counting. By understanding how to determine the number of flip-flops, how to assign states, and how to design the reset logic, you can accurately predict what sequence your modulo-N counter will produce. This systematic approach makes designing and analyzing counters much easier and more reliable.